Before we name a compound, the first thing we need to do is to classify what type of compound it is. And there are two general types of compounds. The first is ionic, in no particular order. The other is covalent. Now, based on what type of compound we're dealing with, there are different sets of rules. So there's one set of rules for ionic compounds, and there's another set of rules for naming covalent compounds. Now, third type of compound would be acids. Acids are actually covalent, but there's a slightly different system for naming, and we'll cover that a little later. So the question is, when I see the formula for a compound, how do I know if it's ionic or covalent or an acid? The answer to that question lies in the identity of the elements. So when we look at the periodic table, all elements can be classified in one of three ways. We have metals, nonmetals, and metalloids. The majority of elements are metals, and here they are. These metals here, along this little stair-step section, these elements are known as the metalloids. And metalloids have some properties similar to those of metals and other properties that are not similar to metals. And our final group are nonmetals. That's all these here plus hydrogen over here. So the classification system is very simple. When you look at the formula of a compound, if you see a metal plus a nonmetal or metal plus a polyatomic ion, the compound is ionic. And then we know to apply the rules for naming ionic compounds. On the other hand, if we see a formula and we notice that the compound is made up of two nonmetals, then the compound is covalent, and then we follow the rules for naming covalent compounds. So let's look at what those rules look like. And before I go further, since I mentioned polyatomic ions, let's talk about what those are. Our definition of a polyatomic ion is a group of atoms that are covalently bonded and have an overall charge. Polyatomic ions are distinguished from monatomic ions in that a monatomic ion is a single atom that has a charge, and that charge can be either positive or negative. If an ion contains a positive charge, it is known as a cation. And the way I remember this is that the word cation has a letter T, and the letter T is kind of like a plus sign, so a cation has a positive charge. And a negatively charged ion is called a dog ion. No, that's not true, but I just couldn't resist. It's actually known as an anion. So here are some examples of polyatomic ions and monatomic ions. So here we have the sodium ion, the calcium ion, the aluminum ion, and the oxide ion. The thing to remember here is that for cations, the positively charged ions, the ion has the same name as the original element. So Na is the symbol for sodium. So when I refer to the sodium ion, it's just called sodium ion. Same thing for calcium and aluminum. However, with oxygen, oxygen is a cation. Oxygen is an anion. For any anion, the rule is that we take the end off of the normal name and we replace the ending with "ide." So oxygen becomes oxide. If you consider any other anion, and generally nonmetals form anions. So consider nitrogen. When nitrogen becomes an ion, the word nitrogen becomes nitride. If you take the elements in group 7A, such as fluorine, chlorine, bromine, and iodine, then when they become ions, the ending is taken off and it's replaced with "ide." So fluorine becomes fluoride, chlorine becomes chloride, bromine becomes bromide, iodine becomes iodide. So that's the rule for anions. All right, change the ending to IDE. For cations, you just name the ion the same as the element is called. Here's a list of some common polyatomic ions. This is not a complete list, but these are some of the most common ones that you'll encounter. So each polyatomic ion has a formula, a name, and a charge. So it's very important that you know all of those, the charge and the formula and the name. The first one in the upper left corner, it's a little unclear, but that's NH4 plus. So, and that's called ammonium. And what that's telling you is that you have one nitrogen atom bonded to 4 hydrogens, and collectively that polyatomic ion carries a charge of +1. So that's NH4 plus. Right, and that charge is really, really important. So these are polyatomic ions, and if we go back to one of the earlier slides when I mentioned how do I know whether I have an ionic compound or a covalent compound, if I have a metal plus a nonmetal, then that's an ionic compound. And also if I have a metal plus a polyatomic ion, that's also an ionic compound. So you should memorize most of what's on this list, but you'll also be able to use it for reference. So if you don't memorize everything on here, that's okay. But as we proceed through the course, as we deal with our topic of stoichiometry and nomenclature, you'll notice that certain of these are very, very common, such as nitrate, hydroxide, carbonate, acetate, this ammonium ion. What else? The sulfate and this bicarbonate. If you know what baking soda is, it's sodium bicarbonate. Okay, that's the name for it, and that's part of the formula. So sodium is Na. The Na ion has a +1 charge. The bicarbonate ion has a -1 charge. So 1 sodium ion to 1 bicarbonate ion, and the charge is balanced. But we'll do more of that in a moment. So here are the rules for naming ionic compounds. The first rule, or this we'll call this rule 0, is that we always put the cation first. And as I mentioned before, the cation just has the normal name of the element, and then the anion has the root of the element name, but then the ending is changed to "ide." And the next rule is that prefixes are not used for ionic compounds. We'll talk more about the prefixes later, but they only apply to covalent compounds. When elements combine to form compounds, they combine in very specific ratios. So when we deal with ionic compounds, the ions have to combine in such a way that the overall charge of the compound is 0. That means that the total positive charge, if we add up all the charges of the positive ions, and the total negative charge must be equal and opposite so that the charges offset each other. So to illustrate this, I have a method I like to teach. I call it the F method. There's also another method called the crisscross method. We'll deal with both of them shortly. If we consider sodium chloride, given the name, how do I write the formula? So now sodium, if we look at it and find it on the periodic table, then we see that it's a metal. And then chlorine is a nonmetal. So I see a metal plus a nonmetal, so that means that it's ionic. So the rule is that I just simply name the positive ion, same name as the element, sodium, and the chlorine becomes chloride. So let's talk about how the charges cancel out here. The sodium ion is in group 1. So side note, all metals in group 1 form ions with a charge of +1. Now in the periodic table, the table is arranged in rows and columns. The vertical columns are referred to as groups. So group 1 would be that group that's all the way to the left. Now hydrogen is in that group, but it's not a metal, so we're excluding it. So sodium, lithium, potassium, rubidium, cesium, all those elements in that group 1, they're always going to form a charge of +1. So I would write the ion for sodium like this. And then we look at chlorine. Now, chlorine's on the other side of the table. So the group that's farthest to the right, those elements are known as the noble gases. And then chlorine is in the group that's just to the left of that. That's group 7A. And those elements are known as the halogens. So the halogens, they always form anions with a charge of -1. So the formula for the chloride ion is written like this. So here we have the formulas for the ions. So Na, because it comes from group 1, it's going to have a +1 charge. Chlorine, because it comes from group 7, has a -1 charge. And I'll show you a simple way to determine the ionic charge in just a moment. But the crisscross method is the easiest method to teach here. So when we look at the charges is actually +1, but we don't write the 1. It's understood. So this is a +1, and we take this here, and then we take this. It's a -1. We're really just concerned with the absolute value. Again, it's understood that it's a 1, even though the 1 is not written, and we put that there. So the value of the charge on one ion becomes the subscript on the other ion. So then the formula for sodium chloride is just simply NaCl. I have +1 and -1, and when we combine the +1 and the -1, the overall charge becomes 0. So to determine the charge of a monatomic ion, really simple. If an element comes from group 1A, 2A, or 3A, if an element's in group 1A, 2A, or 3A, the charge of that ion is equal to the group number. So all the metals in group 1 will have a charge of +1. All the elements in group 2, so magnesium, beryllium, calcium, etc., they're going to have an ionic charge of +2. And if we skip over those groups in the middle there, and we get over to group 3A, group 3A starts with boron, and below boron would be aluminum. Okay, those elements will form an ion with a charge of 3+. Elements in group 5A, 6A, or 7A, the ionic charge is equal to the group number -8. So back to our example of sodium and chlorine, right? Chlorine comes from group 7, so if I take 7, take away 8, gets me -1. So all those elements in group 7A, those halogens, when they form ions, will have a charge of -1. Group 6A, that's that group that includes oxygen and sulfur and selenium. So if you see those as part of a compound, then we take the group number, which is 6, subtract 8, and you get -2. So the charge on an oxide ion is -2. The charge on a sulfide ion is also -2. Group 5A, that includes nitrogen and phosphorus. Again, we take the group number, 5, subtract 8, and you get -3. So a nitride ion has a charge of -3. A phosphide ion also has a charge of -3. In our last example, we had a combination of a group 1 metal and a group 7 halogen, sodium and chlorine, and the charges neatly balanced. But what happens when they don't balance quite so neatly? So let's take another example here. Let's consider magnesium bromide. So magnesium, when you find it on a periodic table, you realize that it's located in group 2. So the charge on a magnesium ion is going to be 2+. I write the formula as Mg2+. Bromine is in the same group with chlorine from the previous example. So since it's in group 7, 7 minus 8 is -1. So the charge on a bromide ion is -1, but we just write minus. So to write the formula, we take the value of the charge. I'm not concerned with whether it's plus or minus, I just want the absolute value. And this comes down here. And then this is a -1. Again, we understand that the value is 1, ignoring the negative sign, and that charge goes there. So when I write the formula for magnesium bromide, I just simply write Mg. The subscript is 1, so we don't write it. It's understood that it's 1, and then Br2. Each bromide ion has a charge of -1, and each magnesium ion has a charge of +2. I need the total amount of negative charge to be equal to the total amount of positive charge. So I need 2 bromines, each carrying a charge of -1, to combine with 1 magnesium, which carries a charge of +2. So again, if you just use this crisscross method, then it's pretty simple. The only thing to watch out for, when we have ionic compounds, the subscripts must be in the simplest ratio possible. So for instance, I wouldn't want something like, for magnesium oxide, magnesium has a charge of 2+, oxide has a charge of 2-. It would be wrong to write Mg2O2. Okay, so the subscripts there, it's a 2-to-2 ratio, which can be simplified to 1-to-1. So the proper way to write that would be MgO. So this crisscross method is very reliable, but you just have to make sure that your subscripts are in the lowest ratio possible. Now you may be wondering, what about those other elements? We only considered metals that are in group 1A, 2A, 3A, but what about those metals that are located between groups 2A and 3A? Those elements are known as the transition metals. These elements right here, from group 3B over to group 12, 2B here, those are called transition metals. Now transition metals, they're metals, and they're going to form positively charged ions, cations. However, many of these metals can have multiple ionic charges. So here are some examples. We have iron. Sometimes iron is Fe2+, sometimes it's Fe3+. Copper. Sometimes it's copper 1+, sometimes it's copper 2+. We have lead. Sometimes lead is 2+, sometimes lead is 4+. And if we consider some others, such as manganese and vanadium, they have even more possible ionic charges. So if I had a compound like iron oxide, how would I write the formula? Just by looking at the name, this doesn't tell me whether it's iron 2 or iron 3. So when we name a compound that has a transition metal, there's an additional rule here, and we need to show what the charge of the ion is. So if you see something like iron oxide, that's actually an incomplete name. So if I give you the name of the compound and then ask you to write the formula, I have to show what the charge is on that cation, and that would look like this. Iron 3 oxide. The Roman numeral 3 in the parentheses tells me the ionic charge of the iron. It does not tell me the subscript that should be on the iron. That's a very common mistake. That Roman numeral does not tell me the subscript for the iron in the formula. It tells me the charge of the ion. Now oxygen, the oxide ion, again, because it comes from group 6A, it's always going to be -2. And now at this point, we can use our crisscross method. We take the 3 from the iron, we put it there for the oxygen, we take the 2 from the oxygen and put it here for the iron, and the formula is going to be Fe2O3. So in this case, we have iron 2 oxide. So the 2 in the parentheses tells me that the iron ion in this compound has a charge of 2+. And again, oxygen coming from group 6A is always going to have the same ionic charge of -2. So here we have a situation, 2 plus 2 minus. We do the crisscross method. It's going to give me Fe2O2, but remember we have a 1-to-1 ratio there, so instead of writing Fe2O2, we have to simplify to FeO. So what about going the opposite way? What if I have the formula and you need to write the name? So let's just look at a couple quick examples. Here we have PbNO4 So the NO3, that's a polyatomic ion. That's on our list, okay, and that's a very common polyatomic ion you're going to see over and over and over again. You need to know that the nitrate ion has a charge of -1, and then the parentheses are there because that nitrate ion, even though it consists of 4 atoms, it needs to be treated like a singular unit. So this formula is telling me that I have 1 lead ion and then 4 nitrate ions. So again, you need to know that nitrate has a charge of -1. This is how I set this up. I call this the F method, and I draw a giant F like this, and I write the formula of the substances involved. Okay, so on this line, this first line, I'm going to show the individual charge, and what we need to know is what is the charge of the lead ion. And you may have figured it out already, but I'm going to show you how I do this. So this is the individual, sorry for my bad writing, individual charge. And then up here, this is total charge. Hold on, sorry. Give me a moment. Total charge. And remember, the total charge has to equal 0. So we're not quite sure about the charge on the lead ion. But again, like I said, the polyatomic ion nitrate has a charge of -1. And because the formula tells me there are 4 of them, I multiply the 4 times the individual charge is going to give me a total of -4. Now, in order to make a total of 0, I need a positive charge that's going to offset that -4. So this has to be a +4. Sorry about that. Let me neaten that up. Okay. So now to figure out what goes here, where that question mark is, we need to simply divide the total charge by whatever subscript is there. Now, since there's no subscript, we understand that it's a 1. So 4 divided by 1 is +4. This tells me that the charge of the lead ion is +4. So then the formula, or the name of this is going to be lead 4 nitrate. Remember, the Roman numeral in the parentheses tells us the charge of the cation, does not tell us the subscript for that metal ion. And in case you're wondering, compound names and element names are not proper nouns, so you don't need to capitalize. You can capitalize if you want to, but it's not necessary. And obviously, if a compound name is at the beginning of a sentence, then you would capitalize it, but otherwise it doesn't need to be capitalized. Now, there are 2 notable exceptions to this transition metal rule. That rule or phenomenon that transition metals can have multiple ionic charges. That is true for the vast majority of them. However, there are 2 in particular that you need to memorize that although they are transition metals, they only have 1 ionic charge. So those are as follows. Those examples are silver and zinc. So when silver forms an ion, it's always +1. And then zinc always forms an ion with a charge of +2. Since these elements always have the same ionic charge, okay, always the same, we do not need the Roman numeral. So when do we use a Roman numeral? When the cation is a transition metal, unless it's silver or zinc. So we use Roman numerals if our cation is a transition metal. We do not use a Roman numeral if our cation comes from group 1A, 2A, 3A, or if it's zinc or silver. The reason is these cations always have the same charge. And that summarizes our rules for naming ionic compounds. Now let's move on to covalent. The rules for naming covalent compounds are super simple. Remember, how do we recognize a covalent compound? When we see a nonmetal plus a nonmetal. Rules are simple. We simply use Greek prefixes to indicate the number of each atom of each element. Okay, you need to memorize this list right here. You're probably familiar with most of these prefixes. Mono is 1, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. There are other prefixes for higher numbers, however, we won't really deal with them, so this is what you need to know. There is an exception, and we'll deal with that in just a moment. So here we have a formula N2O5. So the way we name this, we look at the subscript. So nitrogen has a 2. So 2 is di. The oxygen has a 5. That's penta. And so the way we name this is we put the prefix in front of the element name. Dinitrogen pentoxide. And we have the same idea here with whichever element is second in the formula, in this case oxygen, then we do the same thing with the ending as we did with the ionic compound, so oxygen becomes oxide. And the first element, in this case nitrogen, retains its normal name. So dinitrogen pentoxide. Now you're probably wondering, I thought that the prefix for 5 was penta. What happened to the A? So as a general convention, when we have oxygen, we tend to chop off the A if there's an A at the end of the prefix. So instead of saying pentaoxide, we just call it pentoxide. If there were 4 oxygens, instead of saying tetraoxide, it would be tetroxide. So here we'll talk about one of our exceptions. If you notice the formula here, this is CO, and obviously there's no subscript for the carbon, so we understand that it's a 1. There's no subscript for the oxygen, we also understand that it's 1. And the prefix for 1 is mono. Now the exception is that if the first element has only 1 atom, like in this case our carbon, we do not use the mono prefix if there's only 1 atom of the first element. So instead of calling this monocarbon monoxide, it's just simply carbon monoxide. Now, because oxygen is the second element, we do use the mono prefix. And again, similar to the last one, we don't say monoxide. We chop off one of the O's and we just call it monoxide. This is similar. Again, our first element here is carbon, and there's only 1. All right, no subscript means that it's a 1. Here we have a 2. But since carbon is the first element, we do not use mono, so this is carbon dioxide. Okay, and for the last portion, naming acids. So the first thing is, how do I recognize an acid? And like recognizing ionic compounds, recognizing covalent compounds, we should recognize the acid based on its formula. The key to recognizing acid is that the first element is hydrogen. Here are some examples. HCl, HNO3, H2SO4, H3PO4, HC2H3O2. So notice in some cases there's only 1 hydrogen. In other cases we have 2 hydrogens or 3 hydrogens. The number of hydrogens isn't quite so important, but the bottom line is that when you see hydrogen first in a formula, that is an acid. There are 2 general types of acids. One is known as binary acids, and then we have oxyacids. So a binary acid usually has hydrogen plus a single element. So again, HCl. Generally, it's going to be hydrogen with the halogen element. So HCl, HF, HBr, Hawaii. It's another corny chemistry joke, but you know, HI is the state symbol for Hawaii. But no, that would be hydriodic acid. So another example would be H2S. Again, we have 2 hydrogens, but the point is that it's bonded to only 1 other element. One exception would be HCN. We have hydrogen with a polyatomic ion, but the thing to note here is that there is no oxygen in the polyatomic ion. So these are binary acids. So when we have a binary acid, the name always starts with hydro. and then we take the root of the name of the anion, and then it ends with ic and acid. So let's go back to HCl. So it's going to start with hydro. The anion is chloride, right? We just want the root of that anion name, chlor. So this is hydrochloric acid. And you must include acid in the name, okay? Hydrochloric acid. So if we look at HBr, this is another binary acid. It's going to start with hydro. The anion is bromide, so the root of bromide is brome, so hydrobromic acid. And then sulfur, let's look at H2S. Same format, it's going to begin with hydro. Now, instead of just using the root of sulfur, we actually include the entire name. So this becomes hydrosulfuric acid. Now, naming oxyacids requires a little bit of work, but there's a pattern. And if you can recognize the pattern, then it's relatively simple, or if not simple, it's manageable. So an oxyacid begins with H, and it's going to have a polyatomic ion that contains the element oxygen. So just a couple of quick examples: HNO3, H2SO4, HClO4. So these are all examples of oxyacids. So the key to naming these is knowing the name of the anion. Okay, and so I'll show you a table that explains how to do that. Okay, so the thing I want you to focus on here is this row right here, because a lot of acids come in, as the title suggests, a series or a name. So the thing is that you want to memorize the anion that ends with 8. So examples are nitrate, sulfate, carbonate, chlorate, manganate. Okay. So if you know that one, then all the others are relative to that. So what this is showing you is that if an oxyacid has an anion that ends with 8, we take the name of the anion, remove the 8, and replace it with ic. I'll show you what I mean. Let's consider HNO3. So this NO3 is the nitrate ion. So since this ends with nitrate, or ends with 8, it's going to become ic. So the acid name is going to be nitric acid. So what does that look like in a series? Okay, so let's start with chloric acid. All right, so chloric acid would have the formula HClO3. What you need to know is that this polyatomic ion is called chlorate. All right, so I would have chloric acid. Okay. Now, if you look over here in this column, like I said before, it's relative. So if I memorize chlorate, and I know that chlorate has 3 oxygens, then if we add an oxygen, HClO4, okay, so that has 1 more oxygen compared to the chlorate. It's called perchloric. Perchloric. Now, relative to the chlorate ion, if we take away 1 oxygen, So here we have HClO2. We take away an oxygen, then the chlorate ion becomes the chlorite ion. And if the anion ends with "ite," the acid name ends with "us." So this is called chlorous acid. And then if we take away yet another oxygen, like HClO, then we add the prefix hypo, but the root chlor stays the same.